So good day. It's a pleasure meeting again. And as per what I told you, that we will calculate potentials, electrostatic potentials, due to some very simple cases. The first case that we take is to calculate the potential due to a point charge plus or minus Q. Okay. I can write it better that it is in coping with what the figure has drawn here. It doesn't matter at all. Okay. This is the origin, and we place a positive charge plus Q at the origin and draw a line to the point P and extend it to point P dash. Okay. From the origin to the point P, the radius vector is R, and the distance between O and P dash, which has been chosen as the intermediate point. Okay. This is R dash, and a very small sector of length, which I am taking as delta R prime, R dash, at this point, coming from infinity. Of course, in keeping with what they say, I will take later on assign a charge 1 coulomb at this point. Okay. So let us define as to what is the potential due to this point charge. The potential is equal to the work done in bringing, according to me, a test charge, comma, per unit charge, and like the books write, that work done in bringing a unit positive charge, which I don't subscribe to, from infinity to the point P against the repulsive force, okay, of plus Q. Okay. Then we have this work done is Vp due to plus Q, which is the charge under consideration. So what I do is I write the force on a unit positive charge at P dash, an intermediate point between infinity and capital P, as 1 upon 4 pi epsilon naught Q1 Q2, that is Q into 1 upon R dash square into R dash cap. Okay, you know it, you understand it. Therefore, the work done from R dash to R dash plus delta R dash, that delta W, we can write it here, the minus sign, this is important, because this delta R dash is taken as plus here, but in fact it is minus. And therefore, I can write the force into delta R dash. Okay, force dot dr dx, and that is the work done by definition of work done. The minus Q upon 4 pi epsilon naught R dash square into delta R dash. And if we say that this delta R dash is a small thing like dr dash, and we resort to integrate calculus, then W is equal to minus, this minus sign, minus from infinity to R, this point P, Q upon 4 pi epsilon naught R dash square dr dash, and because integral of x raised to the power of n dx. How much is that? This is equal to x to the power of n plus 1 divided by n plus 1. This is the formula. I just remind you, and particularly the students who don't have a mathematics backup, plus a constant of integration. Okay, so here in this case it is r dash power minus 2, so that will become minus 2 plus 1 divided by minus 2 plus 1. Okay, which means this will become 1 upon minus 1 upon x. Okay, minus 1 upon r dash over here. Okay, so if I put the limits to infinity to be small r, where it has to be brought, then this turns out to be equal to, because the second term will be equal to 0, so 1 upon 4 pi epsilon naught q upon r. Okay, so I can say that the VR, as we wanted to calculate for a charge, plus q is equal to plus q upon 4 pi epsilon naught r. Of course, if this is minus q, then of course this will become minus q upon 4 pi epsilon naught r. So if q is less than 0, V will also be less than 0, but right now the potential is more than 0 because q is more than 0. Well, if I plot the potential and the electric field as a function of r, then we find there are two graphs. This is the graph for the electric field and this is the graph for the potential. Why? Because we have the electric field is proportional to 1 upon r square, while the potential is proportional to 1 upon r. Next, we take up a dipole. So, second item on the various exercises for calculating the potential is due to another entity, and that is a dipole. Minus q plus q, and the dipole vector capital P, whose value is given as 2q into one of the charges. Okay. This is the center of the dipole, and all distances to this point have been with respect to this being taken as center. Okay, from the positive charge to P it is equal to R1, from the center to the P it is R, and from the negative charge to P it is equal to R2. Okay, so this is the simple geometry relation. Now remember that when we were calculating the electric field due to the dipole, then we took the values on the axis of the dipole, or on the equatorial axis or equatorial plane of the dipole. This time we have taken a point P, which can be defined because A is very, very small as compared to R. Okay, so this is defined by an angle theta, which R makes with the dipole moment vector P. Okay, it's very easy from the calculations that we did for point charges, that for this point charge the V will be equal to 1 upon 4 pi epsilon naught q upon r, and for this one it will be 1 upon 4 pi epsilon naught minus q upon r2. Now the principle of superposition holds, and therefore we can add them up and we get capital V is equal to 1 upon 4 pi epsilon naught q upon r1 minus q upon r2. I could also take q outside, there is no problem. Now for this geometry that we have, we can get r1 square is equal to r square plus a square minus 2a r cos theta, and r2 square, which is larger than r. For that I can get r2 square is equal to r square plus a square plus 2a r cos of theta. Now, this is the geometrical construct, but we have made this as the length of the dipole is very sizable, whereas the 2a is very small as compared to r. Yeah, r is very large as compared to a. Therefore, I can write these two geometries as r1 square is equal to, I take r square as common. Okay, then I have 1 here, and when I divide this by r square, I get 2a cos of theta upon r plus a square upon r square. And similarly, now this a square upon r square I can take as approximately equal to 0, and therefore we are left with what? We are left with r1 square is equal to r square 1 minus 2a cos of theta upon r, like that. And with the similar argument for r2 square, I get r square 1 plus 2a cos theta upon r. Okay, so it's nothing difficult in that. Now we need from this to find out the value of 1 upon r. So I reverse that and take the root over. So for 1 upon r square, I will get 1 upon r. And for this part, I will get 1 minus 2a cos of theta divided by r raised to the power of minus half. Okay. And if we use the binomial theorem as a linear approximation in the binomial theorem, using binomial theorem, just we write like this, UBTH, and taking the linear approximation. So what I will get? I will get 1 upon r as it was, 1 minus the power minus half into the argument 2a cos of theta divided by r. So this will work out to be equal to 2 will cancel with 2, minus into minus will become plus, and what I am left with 1 upon r into 1 plus a cos of theta upon r. Okay, it's not very difficult, very easily obtained. So, and similarly 1 upon r2, going through these steps, I will get this as minus a cos of theta. Okay, so let us write the value of v at this point p. So it will turn out from here, now I am taking q as a common factor. So I am just writing v will be equal to q upon 4 pi epsilon naught. Okay, in bracket 1 upon r1 minus 1 upon r1. Okay, and this is larger than this. Anyway, so if we now compare and we subtract this value from this value, so 1 and 1 will cancel, 1 upon r will be as such, and here I will get a cos of theta upon r plus a cos of theta upon r. So this becomes 2a cos of theta upon r. Okay, into of course q upon 4 pi epsilon naught into r. Okay, so if we assimilate all these things together, here what I get now q into 2a has been taken as p, the magnitude of the dipole moment vector. So this q into 2a becomes equal to p, then cos of theta divided by 4 pi epsilon naught r into r, which is equal to r squared. So this is the value which we will obtain. Okay, now look into this expression. The physics starts when the expression ends. Okay, so what we find is that there are two factors. One is that v is proportional to 1 upon r square. Okay, and the other is that v is proportional to cos of theta. So theta also plays a role under the condition that R is far far larger as compared to A, we have this expression, and I will just combine these two together. Okay, so V is proportional to 1 upon R square, V is proportional to theta. Okay, now let's use this and ask some question. What will be the value if I take the point P on the axis of the dipole, on the side of the plus Q? So when we do that, this theta becomes equal to 0 and the cos theta becomes equal to 1. Okay. So the value turns out to be equal to, here, look here, 1 into P upon 4 pi epsilon naught R square. But if I take the value on this side, the P is shifted on this side, then this angle that it will make, now it becomes 180 degrees or pi radians, for which the cos of the angle, cos of pi is equal to -1, and therefore what we are going to get on this side, nearer to the negative charge, that there will creep into it minus sign. Okay, that's all. Simple set of arguments. So I'll get the value on here on the axis of the dipole, on the opposite direction to the P, because P is the direction from minus Q to plus Q. That is what we know. So if it is in this direction, then we will get V is equal to minus P, okay, upon 4 pi epsilon naught R. Now, you will ask me a question, and you will ask, sir, or maybe you can call me Mr. Rizvi, no problem. What will happen on this line, which is the equatorial axis, which is the equatorial plane which passes through this thing? And the answer will be that the value of V on this plane will be equal to 0, simply because cos of 90 degrees is equal to 0. Okay. So that way, friends, starting with the equations that we derive, okay, after the approximations that you must have in your mind, and the most important approximation is that R is very very large as compared to A. Now one more thing I will tell you. If suppose we are talking about theta is equal to 0 degrees or theta is equal to 180 degrees, in that case the value turns out to be equal to P upon 4 pi epsilon naught R square. Now remember, go back to the case of the electric field due to a dipole, and there for the electric field due to the dipole we obtained a proportionality with 1 upon R cube. But this time, in the case of potential, the proportionality is 1 upon R square. Okay. And if you give it a think, a little bit of a think, then if I integrate 1 upon R cube, I will get 1 upon R square. And if I differentiate 1 upon R square, I will get R cube. So that is the kind of relationship that exists between the potential and the electric field that we will shortly visit. Okay? So, I repeat, the results that we have obtained, the result I have obtained by using the geometry. From the geometry we take the approximation, linear approximation, and then we ignore this a square upon r square because this is infinitesimally small. I get this result. For r2 square, I get this result. From these two results, I write the value of 1 upon r1 square and 1 upon r2 square. take the square root, and through a simple set of steps, using what? Using the binomial theorem and using the linear approximation, we arrive at a compact result which gives us, with the value of 2a into q being equal to p, I obtain p the constant for a given dipole. 4 pi epsilon naught is also a constant. The only two variables are r and cos theta. We obtain these results, then interpret these results for the long side on position, which is called the equatorial axis, the axis of the dipole, and the broad side on position, which is known as the equatorial axis, the equatorial plane, and we find that the value of the potential is equal to 0. Well, I thought that I will include the potential due to a system of charges, okay? But these two things, is potential due to a single charge and the potential due to a dipole, is enough for a lecture at a stretch. So I propose to take up the next item, that is the V due to a system of charges. What it means? It simply means that there are so many charges and there are so many potentials due to individual charges, and we will apply the principle of superposition and calculate those potentials algebraically. Okay, not vectorially, because there is no question of vector here. So it is the positive and negative quantities which are coming in the algebra that we have, and therefore we will do it. How come? We will do it algebraically, taking the plus and the minus and. Just like the in simple, if you want to know as to what is the total charge, then the positive charges and negative charges put together, and we calculate the net charge, whether it is positive or whether it is negative. So we stop here, okay? And now on your screen appears what I had written over here, UQVA, which means U question and V answer. I am longing for your questions and would love to answer some of your questions if I can. Okay, just ask logical questions. Okay, please don't ask metaphysical questions, because we are doing physics, and I will enjoy answering you the questions related to physics, derivations, and their interpretations. They are important, they are very important. So please, once again I will say that visit this lecture, listen to this lecture, look at this lecture twice at least. Okay, you are no expert.